Yeah.
Okay, bro. Does everyone have access to the Back to Basics notebook? So I've updated it from part 6, which we did last time. What were we doing last time? We were doing a little bit of graph theory. So we had downloaded our 3D structure file of the protein, and we had used the KD trees algorithm to find nearby neighbors for each of the atoms. And then we assumed that if it was within a certain distance, we assumed that it was a covalent bond, which might not always hold true. And then we used that to construct a graph for the protein. That is a representation which is based on who is connected to who rather than who is positioned where in space and so on. So we were working with that, and then we were looking at each atom's neighbors and seeing how well that corresponds with the atom identities in the PDB files. 6.1, atomic neighborhoods, unique elements, and then at the end of that tutorial, we touched on objects and classes, which is a pretty important aspect of Python, being an object-oriented programming language. But so far, in all of Python clubs, since how long I've been doing this, I haven't actually taught classes and objects and so on. So yeah, where did we go? What is an object? An object is a variable in memory with a name, and in Python, it's an instance of a class with where a class is a template of an object. So yeah, we've worked with objects before, perhaps without knowing it. Like for example, a pandas data frame is an object, and the class will be the pandas data frame, and then we'll initialize it with some data and so on, and it has its own attributes and methods. A method being a function that belongs to an object, and an attribute being some data that belongs to an object. So we went through a couple of attributes and functions that the NetworkX object has. And we very briefly went over how to build a class. So we made a test class, which has, it pretty much, or at least in this case, pretty much just wraps 2 different functions. It doesn't actually store its own data, but it can potentially be a way to sort of like bundle together a bunch of functions in the same way that you might bundle together like a bunch of remotes for the telly so that they're all in the same place or something like that. So we can run this and access functions like that. But so that's an example of an object that doesn't have its own data. And then we also built an object that did have its own data. And we got our first taste of the double underscore methods, aka dunder, in popular nomenclature. So I suppose this is a good time to explain what on earth a double underscore method is. Sometimes they're called magic methods within Python. It's a sort of a reference to a Python built-in method. And in the case of creating an object, the double underscore initialize is the function that is run when you call an object like this. Initialize runs now on that line. So yeah, when we create our object like this, what has happened? X is not defined. Okay. So the problem here is I haven't been very clever about this, and I will. Okay, yeah, no, I think I will go through very quickly what I've done here, and then I'll touch again on initializing objects with parameters in just a sec. Okay, so when you create an object, if you want it to store data, then you will certainly have to run this initialize function, which will run as soon as you initialize the object. So for example, here, that's an initialization. Now we have an object X, which is based on this template, another class up here. and it contains this data, this little emoji here, and it will also contain the variable x, x.x, that will be within it, which will be equal to 3, I suppose. I fed it 3 to start with. So there's something unusual about the init function, apart from the fact that it has the double underscore method built in. It also takes in this argument called self, and you'll see this reference to self sort of throughout the class objects. So when you're defining a class, all functions that you define within that class will automatically take in a first parameter to any function that you give them of the class itself. There's nothing magic about the word self, it's just convention, but I strongly recommend that you stick to that convention to avoid confusing people who are attempting to read your code. So this function runs, and you'll notice that whilst it takes 2 arguments, we've only fed it 1, and the self argument that would go here, nice spelling there, is fed to it automatically. And then setting the variable self.data sort of pins that piece of data to this particular class. So that was a bit of a rushed explanation. Let me go into the meat of the tutorial that I have prepared today. You might see the odd note here and there that I put in for myself, like for example that, and then didn't complete. Apologies for that. Probably best ignore. I recommend that if you want to find out more and more accurate explanations about classes and so on, then follow this link to the free ebook Python Notes for Professionals, which is very strongly recommended. And check out chapter 38, which is all about classes, written in fairly short form with lots of examples. It's very readable, very dip in, dip outable, and it's free. So I recommend very highly that you check that out. So I mentioned earlier that the double underscore that flank each side of these special functions sort of denote the special Python built-in functions. Perhaps later I'll link up some articles with more information about this sort of dunder method. But for now, we are going to ignore the rest of the special functions that we have available to us in Python, and we're just going to focus on the initialize function, which, as I mentioned earlier, is used to initialize an object when you create it. Okay, so typically when you create an object, you'll type the name of the class. In this case, the name of the class is test, and then you'll follow it by parentheses or brackets, and maybe you'll fill those brackets with parameters to give to the object to sort of set variables and so on. So for example, T2 here, in the parentheses, it's initialized with the number 5. And when you run this sort of the name of the class followed by parentheses, and optionally with or without variables, depending on the object itself, the init function that we looked at earlier with the double underscores, like that, that's what runs, and it constructs the object, doing a mix of sort of setting attributes, storing data, and making sure that everything is in working order. And as I mentioned earlier, we have constant reference to self. And like I mentioned also, self isn't a magic word in itself, but it's just a convention. And it's how you sort of refer to the object itself. If you want to pin a variable to that object, then you'll be using the word self an awful lot. And shortly to follow, I'll show you examples of how they might look in the wild. It took me quite a long time to get my head around this in the beginning, so I'm hoping that examples. Well, I found examples pretty helpful when I was learning, so hopefully you do too. But yeah, any questions, then shoot them my way, and I'll do my best to answer. And if I can't, then I might refer you to some online learning resources. Okay, yeah, as I mentioned earlier, all functions defined in a class automatically take in a reference to the parent object, self, as the first parameter. You can use that to set internal variables and let an object refer to its own variables and functions. Cool. This link has a very nice succinct explanation on self right here. And if you're not already aware of Stack Overflow, it's probably the #1 go-to for programming errors. Answers are upvoted and so on, so you can sort of gauge their validity. And the user Crispy has got a quite nice explanation of the self variable. Let's dive into it. The self variable represents the instance of the object itself. Most object-oriented languages pass this as a hidden parameter to methods defined in an object, but Python doesn't. You have to declare it explicitly, and when you create the instance of the A class, you call its methods, and it will be passed in automatically, as in this example here. The init method is roughly what represents a constructor in Python, as opposed to constructors in other languages. When you call A bracket bracket, Python creates an object for you and passes it as the first parameter to the init method. So it'll be passing the self to the init method and so on. Any additional parameters will also get passed as arguments. And in this specific example, it will cause a problem. Okay. What did I do here? Okay, so I've made a little example down here. I make a class called test, and I start with the initialize function, def __ init. And like I mentioned earlier, the first parameter that will take in is self, or at least as you define the function, and then optionally a parameter here. And as we initialize the object, say down here, then this is the function that will run. And in this line, self.p equals param, then whatever this variable is, which in this case is the 5, because remember the self part of the function is automatically passed to the test object. Self.p gets set as a param, and that's basically the gist of how you might save a variable to an object. Like, for example, a couple of weeks ago, I was messing around with a sort of data from a nematode brain. So I'd create an object, and then I'd set one of the variables as the graph of the nematode brain, and so on. Maybe I'll revive that for a future lesson. That could be interesting. Exit out of that. And then you can see underneath we also have a function. So like I mentioned, all the functions as well as the init also take in this self variable, and if you want, other variables as well. And so since this doesn't take in any variables itself, but it does refer to self.p up here. So in this case, self.p is the number 5. And it has to be self.p because that's the only location that this parameter actually lives at, and then it returns that times 8, so it will return about 40. Okay, that's quite a lot of rambling, so let's move on to exercise 7.1. What does exercise 7.1 ask of us? Well, over the last couple of weeks, we were gathering various bits of information about our protein in question, the P450BM3. So somewhere up in this notebook, we have its sequence. We have a data frame that contains all of its coordinates. And we also have a graph of all of the short bonds. I think it's called G short bonds. So your task is to create an object that will initialize and set the sequence as one self variable, set the data frame as another self variable, and set the graph of short bonds as another one. To to save you from looking these up, I've put the names of the variables in here. If you haven't run all of the cells already, then I recommend maybe do run all or run before, just to make sure that in your runtime, the variables actually are set. And I'll give you a couple of minutes to do that, maybe 5 minutes, which will give me just enough time to make a rendition of the two laughing boys, I think it's called. So I heard this painting got stolen fairly recently. Where from? But just in case the museum never recovers it, which museum is it? Then I suppose I ought to have a backup for them for just in case. So I'll do that. Oh, 7 seconds left. Might as well save this painting. Two laughing boys. Cool. Okay. Okay, so the aim of the exercise was to make a class that contains a couple of variables. So it doesn't need to contain any functions, which is good. I've just made a text cell. Let's go through the answer of that very fast. I'm going to call this class protein. Declaring a class is a little bit like declaring a function. Optionally, you can have parentheses here, but we'll get into the how and why you might do that in just a bit. So within the class, we're going to have, of course, our initialize function. And what is the first parameter that we're going to pass to init? It's self, always self. I mean, if we really wanted, we could pass it something that isn't quite self, and it wouldn't throw an error. But for the sake of good programming practice and making our code actually like readable by other users, we're just going to stick with the conventions for now. Okay, so the variables that we want to include are, I keep doing that. Let's put in a doc string up here. Contains a data frame, a graph, and a sequence. Okay, so let's start with sequence. Self.sequence equals s. If you had done sequence equals s, that wouldn't have been syntactically invalid, but if you were to initialize the protein object, p equals protein, and then try to access the sequence attribute, you would find that there is no such sequence. But if you put self before it, then you can access it. You'll see here that this is the unclean version of the sequence, so not to worry. I seem to remember we had a clean sequence function somewhere up there. Sorry for not mentioning that in the problem specification. And now we have the attribute clean sequence as self.seq. Okay, cool. Well, then extending from that, we can have the attribute self. Let's be imaginative and call it PDB coords equals df. So now if we were to initialize it and find the PDB coords attribute of our protein object, then it contains this data frame, which is cool. And last but not least, self dot, I need to get better at typing, I think. Short bonds graph, let's call it. That's a fairly descriptive name. Equals G short bonds. Fantastic. Okay, and then similar to before, we know that it does indeed contain all of that. Okay, well, hopefully no one had too much of an issue with saving objects to, or sorry, saving attributes to an object. The main things to remember are within the initialize function, it must have self passed to it as a first argument, and then anything that you want to be saved to the object has to be declared as self dot, and then your variable equals this. Everything else is just not remembered, pretty much. So I suppose one way to think of this is as a bit of like a save statement. To save some data to this object, you declare self dot and then declare a variable as you normally would straight after that. Okay, section 7.2. Initializing with parameters. Okay, so quite often you'll be wanting to use the class function more as like a template for an object, and the actual data that the object contains might sort of vary from instance to instance. Like for example, say we wanted to call this protein with, or this protein object with like a different protein, say a different PDB file, a different sequence, and so on. Well, in that case, then it'll be useful to be able to pass parameters in here. So like, for example, it'll be nice if we could say we want our protein sequence to be this one, and we want its coordinates to be coords 2 or something like that. So in that case, then you would be wanting to declare your init statement with additional parameters available. So in this case, I've made a test object, and in the initialize function, after the mandatory self argument, I've got param1 and param2, which means that when I initialize it down here with the params 100 and a string a, param1 and param2, 100 and a respectively, get saved as self.p1 and self.p2 respectively. So similar to how you would sort of allow extra variables to be passed to a function, you can do pretty much the same thing with an object, and it's very common for that to happen. And yeah, recommended, I suppose. I mean, it's more useful to have a slightly more flexible object, but then it depends on what your use case is. At least there's some flexibility. Sometimes you might want to have optional parameters or parameters with default values, because sometimes you don't always have that much information available to you, or maybe I have an object that takes in like 10 different parameters, but it's fairly safe to set some of them to default values. Well, to set a default value, same as you would in a function, in the parentheses following the function name, you set the name of the parameter that you want to be passed to it, and then to declare a default value for it, you declare that, say, param1 equals 100. Now, in the case that I don't declare param1, it will default to 100. But if I explicitly say param1 is 99, or I say just initialize it with 99, then automatically that will override the default value that I have here. So that's a pretty useful one to know about, especially if you're dealing with objects that have, you know, multiple attributes or multiple potential attributes, but they can be defaulted to a particular value or a none value as well. It's quite common, for example, with param2 here, its default value is none, just in case I don't have information for it. Okay, so that's a brief primer on initializing with parameters. And like I mentioned, it works for functions too. Let me correct that spelling error. There you are. Okay, methods, where are we? Methods. Okay, so we've covered the initialize method of objects. Now we will look very briefly at methods or functions within an object. So the specification of a function works pretty much the same as functions that you've learned to write elsewhere, only that there's the mandatory self argument again. And then also, if you want to refer to or set a variable that's specific to the class, like for example, say I wanted to refer to x here, then like normal, you'd have to refer to self.x to actually get access to that variable. So what have we got here? We initialize our test object, which has a default value for param1 as 2. but we've explicitly overrode that as 5. What happens when we initialize it? Self.x gets set as the result of this internal function, self.fn param1. Okay, and what's self.fn? Well, first you'll notice that to access that function, I have to say self.fn. And if I were to access that from outside of the object, then I'd have to type the name of the object, in this case t, after it's been initialized, and then .fn in that case. So what does .fn take in? So it'll take in the param1, which in this case is the number 5, and returns the square of that. So that will return 25 in this case. So self.x or t.x in a specific instance is going to be 25. So that's an example of a method that makes, or an internal method that is used to create an internal state or an internal variable. Often these are quite useful if you've got some fairly complex objects or attributes inside your object. Sometimes they will require a function to create. So that's an example of when something like that might be useful. So I talked about setting internal variables using self.this or self.that in the init statement. But it's also possible to set internal variables to a function outside of the init statement. Like for example here, I've got a function called setY, and it takes in a parameter y, and from outside the init function, it sets self.y as y. So in this case, I initialize the object, I set y as 3, and it's worth noting that you can also adjust and set attributes externally as well. So for example, I take t.y here, which in the last line I set as 3, and I add to that 1. So that's an example of how you can modify existing variables to a class. And you can add new variables to a class new attributes to a class from outside of that class after it's been initialized. And that's called monkey patching. It's a sort of a quick and dirty method. It makes your code like a little bit more difficult to follow for someone else reading, but it works. So yeah, I suppose you'll have to weigh up whether or not it's worth doing in each use case scenario. If someone's going to be reading your code or using your code, then maybe try and be neat and set these variables internally, else you can set them externally. Okay, exercise 7.2, I forgot to put a title in. So yeah, often if I'm making like a fairly large object with quite a lot going on, I make quite a lot of references to self, both for internal variables and internal functions. And one of the main errors that I get is forgetting to refer to self before referring to either a function or a variable. So I was trying to think of an exercise where we create a class that sort of relies on a lot of typing self, and so on, just to sort of drill to try and avoid that sort of error. So I've started to build a class called particle. It contains a short NumPy array that's got enough space for X, Y, and Z coordinates. And it has got a XYZ velocity as well. And you'll notice that I've left some empty functions here. That's what this pass here means. Pass is a way to leave a function empty just so that you can sort of make a skeleton of say like a class, a function or whatever, and then sort of come back to flesh it out later without sort of it being invalid syntax, syntactically invalid. Okay, so here's a description of what the function should contain. So I've started this update velocity function, and it takes in an optional parameter of direction, which will be similar to this, a 3-member NumPy array. But if direction is not specified, so there's an if statement in there, then the new direction of the particle is this. What is this? mp.random.normal. Well, it returns a array, a NumPy array with 3 elements with a number sampled from a normal distribution with a mean of 0 and a standard deviation of 1 and 3 elements. So for example, that will be its direction if direction is not specified, or that. Or that, you get the idea. So if direction is not specified, then the new direction of a particle is this statement, the random normal. Otherwise, the direction is input as a 3-element NumPy array, just like this. And you would use the direction to nudge the velocity by adding the 2. So in layman's terms, then I suppose, you would update velocity plus equals direction. That's what I want out of that function. And then we have a second empty function called step. Step being, so say this were a particle in a simulation, then this step function would execute at every time step, every frame of the simulation, if you like. And what happens there? The coordinates here will be updated by the velocity, pretty much coords plus equals velocity. That's what I want out of those two. I've left some lines in the bottom so that you can see the output as you run it. So the particle is initialized as p, its coordinates are printed out, its velocity is updated with this array, a step is done, and chords are printed out again. If anyone has any questions, then give me a shout, and in the meantime I will be painting the girl with the pearl earring. And I need to set a timer. About 15 minutes ago, Steve in the chat asked about setting attributes to global variables. I've got to say I'm a little bit uncertain about that one. I think from inside a class, I don't think you can set global variables. What's a global variable? A variable that is remembered outside of your function or your class. But I might be wrong about that. So I'm going to leave a question mark by that for now. We'll come back to it at the end of the exercise. Let me finish drawing this lady.
That is essentially what you did when you set your first example.
Okay. Do you remember which example?
The very first, this one.
This one. Protein.
So self.seq equals clean sequence.s. S is a global variable in this case.
Ah, yeah.
It's not recommended because users of the class may not have those global variables in their particular situation.
Yeah, that's a very good point.
So it's nearly always set as the parameters of the init method.
Yeah, so it'll be more sensible then to have S PDB chords going in.
Exactly, that forces the user to provide the actual parameters they want.
Yeah, that's a good point. I think so. So with most of the exercises, I put some of the answers in. I can't find it, but I put the answers in one of the sort of backup files, the import back to basics answers files, whatever it is. But yeah, it couldn't exist outside of this notebook. So yes.
And it's related to the idea that object-oriented programs should have self-contained classes, so they that they are portable.
Yeah, that's a good point. So this at least, whoops. So this class in this state wouldn't be portable to another script because that doesn't exist in another script, nor does that, or that might be something completely different.
That's exactly right, yes. So it's a bit of a no-no as far as object-oriented work is concerned.
Okay. Naughty James. Yeah, sorry about that, everyone. Well, we live and learn, don't we? Oh, that's the timer done. I didn't even finish the girl with the pearl earring. Dang. All right. Well, I'll finish that in my own time, I think. Okay. Let's have a look at this exercise. I'm trying to remember what I actually set for you. Attributes, particle. Yeah. Okay. So unlike the protein object that I set before, which did contain global variables, which, as Steve mentioned, is a no-no. This particle variable doesn't rely on global variables. That is, variables set outside of this class. Internal variables. It has an initial coordinates of 0 and an initial velocity of 0, and we want to update the velocity. So whilst many root functions might end in return this or return that, we don't actually need to do that. We just want to update the internal state. So I mentioned that direction is an optional parameter, but if direction is none, then it will default to something else. So we need an if statement. So if direction equals none, then what do? Direction equals np.random.normal. So sample from a random normal distribution with a mean of 0, a standard deviation of 1, and 3 elements. Cool. Okay, so if direction is none, not provided, then direction will now be equal to this. Otherwise, just carry on, I suppose. And now we want to update velocity. So velocity plus equals direction. Sounds good enough to me. But what have I missed out? I've missed out self. Self.direction. Sorry, self.velocity plus equals direction. Cool. Well, let's see what that does when we run it. Any errors? Yeah. Oh boy. Yeah, I really should have. Okay. So what's the problem here? The truth value of an array with more than one element is ambiguous. So the problem is happening on this line. It's the logic test to see if direction is either none or a numpy array, and it's having real trouble saying that comparing a numpy array with a none type object. So how do I get around that? Well, I could do if type, and I think it's none type, isn't it? Okay, that seems to work. So let's break down what's happening here. So the possible values of direction in the expected use case are either a numpy array or a none type object. So rather than directly comparing the object, I'm comparing the type of object, and that should return a value none or not none. And then we can carry on as normal. Bro, okay. And how about this step function? Well, what does step want? Step should update the coordinates of the particle by adding the velocity to the coordinates. Okay, so no if statement needed here. So hopefully we have a velocity, self.velocity. And we also have self.coords. Okay, these are the two variables I suppose we're working with. Adding the velocity to the coordinates. Coords plus equals velocity, self.coords plus equals self.velocity. Okay, and let's run that and see if that works. Yes. Cool. And then how might we use that in an actual context? Well, we might do for I in range 5, p dot update velocity, we'll give it nothing so that it gets a random direction each time, and then p dot step, and then let's see where it's at by printing p dot coords. This is how you might access an attribute of the object, p dot coords, the coords that belong to an object. So when you're accessing something externally, you don't need to type self at all. Oh no, what have I done? Okay, so the problem is that the direction and the numpy random are not playing together well. P dot velocity, was it? Okay, I think I know the error here. Same kind. I think the problem is that these are integers and these are floating point numbers. I think that's the problem. So maybe I need something in here to ensure that the direction is definitely a float. So dot as type float, maybe as type is valid numpy. Okay, well, we're almost coming up to the hour, so in the interest of time, I'm gonna ignore these errors and maybe come back to it in the next lesson, in favor of talking about inheritance, which is a pretty important feature of object-oriented programming. So, for example, say we've created some particle objects, and we want to use that as a template for expanding upon that and creating custom versions of a particular object, then that's exactly when you want to use inheritance. So you'll initialize an object, and just like that, you can have it inherit all of the attributes of a more complex object or a fairly complex object, and then you can quite easily add additional attributes to it rather than copying and pasting all of the code for that particular object and then tweaking it here and there. So it makes it quite easy to expand quite quickly. It's all very, very scalable. Okay, so I mentioned earlier that you might have parentheses as you declare a class, and that is this inheritance is exactly when you'll be using these parentheses. And to those parentheses, you'll be passing the object from which your new object is inheriting the attributes and the methods from. Okay, so let's have a look at this example here very quickly. I create a class called base particle. Why do I call it that? It's the template class upon which our next class will be based. It initializes, it has some coords, it has a step function, which given what happened in the last exercise, it probably won't work, but hey ho. And then we have a second class here called charged particle, which is very similar to the base particle, only it has an extra attribute, charge. But what's happening here? There's some parentheses, and within those parentheses, we put the name of the class from which it is inheriting. So that's one of two things that you need to do when you inherit attributes from another class. So you pass the parent object in through the parentheses. And additionally, within the initialize function, you'll need to use the special built-in command super. What does super do? Super is a way to access the parent class and initialize that. You'll see just below that in the first line of the initialize command, I've got super. Doesn't need any arguments, not in Python 3, Python 2 maybe, but probably you won't be working with that. And then I call double underscore in it, double underscore, with no attribute, sorry, no parameters, because this requires no parameters. And you'll see that when we run that command, then suddenly this charged particle inherits everything that the parent class once had. And then after that, we can add additional stuff. So let's take a look. C equals charged particle, and I'm giving it the charge argument of -1. So that'll be here. Self.charge will be -1. And we can print the coordinates. So you'll see that in the charged particle, I don't actually declare a coordinates variable. That's declared in the parent class. But now the child class, charged particle, has that as well, which is cool. And it also has the method step available to it. So we can step and then print the coordinates here. And it seems to work just fine, unlike the one before. Okay. I suppose it's just as well that I didn't try and shoehorn an exercise in here, because we are at the hour. If anyone has any questions regarding classes or any of the material we covered today, then feel free to send me a message. I very highly recommend Python Notes for Professionals, Chapter 38, for more information on classes, or just the book in general for any non-specific Python questions you might have. It's my #1 go-to reading material for all Python problems, unless it's like module specific or whatever. I might or might not do Python Club next week. I've got a thesis meeting from 11 till 12 next week, like right before Python Club. So I'll see how it goes and I'll let you know. And I may switch topics at some point because seven episodes of Back to Basics is quite a lot, and yeah, I think it'll be quite nice to move back to data analysis and that sort of thing at some point soon. Perhaps I could gather some lab data specifically for Python Club and start working with that. I'll let you know. Yeah, before we leave, any questions, comments, or any other items Python related that anyone wants to bring up? Okay. Well, in that case, I'll stop recording there. Thank you very much, everyone, for coming, and maybe I'll see you next week. Bye.
Cheers,
Bye,
James.
everybody.
See you later.
See ya.
Thank you, James.